Dilip Kumar from EDB.
Thank you, everyone. Yeah, so my name is Dilip. I work for Enterprise DB, and I've been working with PostgreSQL core since Postgres version 8.1. It's like since 2008. And today I'm going to talk about one of the challenging or PostgreSQL problem, which generally we find very rare. Means we don't see it coming very frequently, but nowadays I'm getting such problems from customers, and we are also seeing these problems in the PostgreSQL hackers. So, and there are quite a lot of questions from the customers and users who are facing the problem that what is going underneath, like what is the reason behind that problem. So, today's my idea about this talk is to introduce those problems and understand some surrounding around that area, and also dig deeper and understand what is going on and what is the cause of that problem. So this is agenda of my talk. First, we'll start with the introduction of the first problem. Basically, I'm going to cover two problems, and both are somewhat related to Postgres SLRU implementation. So first, we start with the introduction of the first problem. Then for understanding that problem more in detail, we need to understand some logic around Postgres snapshot implementation, PG subject SLRU, and visibility, how the visibility happens in PostgreSQL. And then we will go into the actually understanding the problem of what is the real problem of subtransaction cache overflow. And then we'll see that with presence of the long-running transaction, how that problem become even worse. That is all about the first problem. Then we'll go into the introduction of the second problem. I'll just show some tests, what I have done to, and how I simulate that problem. Then we'll understand something about the row locking and MultiZect ID in PostgreSQL to understand that problem more. And then finally, we summarize our talk. So this is my test, but before going into that detail of what test I have done, I just want to take a quick vote that if you see the bottom half where we have seen that red color Subtrans SLRU and Subtrans buffer. So how many of you have noticed such wait event ever in your use case or with your customers? So yeah, that proves that this is very rare because only one person raised hand. So this problem is like sometimes it can become bad, but it is a bit rare because generally many people don't have such use case. So now we are going to understand this problem more in detail. So this is my test. I just run a PG bench test with you can say 64 backends and 64 clients, and with fairly powerful machine which have 128 cores. So it started with normal read-write transaction. It started with, as usual, generally we see 30 to 32,000 TPS, and it started with the same TPS in my setup also. Then I started one more transaction, or you can say one more script, which what it does is it start a transaction, create more than 64 save points. Why 64? That we will, I think once we go deeper into the problem, we'll understand that better. More than 64 save point, and each save point do some write operation, just so that it get a subtransaction ID. And I run that script from a single thread from another PG bench session, and it keep running. It start a transaction, do that operation of 64 save points, commit it, and then start again, frequently in a loop, you can say. So with that, I see that performance dropped almost to 50%. It's from 32,000, it becomes 16,000. Then, in addition to that, what I have done is I started one more session, started a transaction, assigned the transaction ID to that by doing some simple write operation, and then you can see what happened to the performance. It's like system came to its knees, like it's just 200 TPS from 32,000 TPS. So the whole idea of this talk is to understand all these think that what is happening, why the system is behaving like that. So first thing, and generally when we see nowadays problem in PostgreSQL related to performance, we try to observe the wait events. So same thing, I try to simulate some of the problem which I already knew, but yeah, so I again try to check what happened in wait events. So I see that Subtrans SLRU, Subtrans buffer, those are one of the peak wait events in the system. So for understanding this problem, we need to little bit have some idea about the snapshot and visibility check, and from that I think we can understand this problem better. So I'll start with snapshot. So why do we need a snapshot in PostgreSQL or for any database? So basically, when you start a query, if you talk about read committed isolation level, when you start a query, for getting a consistent view of the data, you need a snapshot. And what do I mean by consistent view of the data is like once you start a query, it should not happen that read committed means you just see the committed data. You start a query, you just keep reading the tuple, and if tuple is committed, you just assume it is committed for you. Then what will happen? That you might start read one page, you see some couple of the tuple, and those are the transaction which are inserted is not yet committed. You'll see, assume that you should not give it out. Then you read further pages in sequential scan maybe. Then that transaction who is concurrent to you is committed now. So you'll give the partial data of that transaction. So that should not happen. You just need to create a consistent view. The snapshot is a view where you assume that what you decide when you start a query in read committed isolation, you decide that what will be visible to you, what will not be visible to you. You set that rule at the taking the snapshot, and that throughout the query execution, you follow that rule. So what we store in the snapshot is, we store a range of XIDs and sub-XIDs, which tell us that which XIDs is concurrent to us. So basically, we go through all the backends, and from each backends, we take a currently running XIDs and also a sub-XIDs and keep into some array. And we also set a boundary like xmin and xmax for the snapshot. It means we don't want to keep the XIDs in the system like which run forever. We know when we're running through the backend, we know that which is the smallest running XID in the system. So once we know which is the smallest running XID, it means below that XID, you can always assume the committed for you. All the XID which is smaller than that, you can assume committed, because when you took a snapshot, this is the smallest transaction ID was running. And then you also have the latest committed XID variable available, right? So that you can set as a xmax. So any transaction ID which is bigger than this particular value, you can always assume it is running for you, it is not committed for you. But what happened to the XIDs which is in between xmin and xmax? Because in that range, it is possible that some are running and some are committed. So what you will do is, in that particular range, the XIDs, whichever you see in backends and sub-XIDs, you store into your XIP array and sub-XIP array. So each backend have its current XID information, we directly copy into array, and along with that, there is shared structure where with respect to each backend, we have a cache of 64 sub-transactions. That many sub-transaction information we keep into the backend, so we can directly get those into the snapshot. Now I want to introduce a little bit more about the PG Subtrans SLRU. And once we know these two concepts of snapshot, visibility, and Subtrans SLRU, I will connect them to show exactly what is happening in the problem. So PG Subtrans SLRU is nothing but a mapping from a subtransaction ID to a parent transaction ID. So with any transaction ID in the system, we have 4 billion transaction ID range. For each range, you can each XID there is a 4-byte information available. So from that, you can directly map into a slot that exactly which page of the SLRU that XID will be there, and you will for that XID slot, you can find its parent XID. So this is mapping from the sub XID to XID, and if it is slot for the top XID, then it is just a zero field value. It means you can assume it is top transaction ID. And on top of that disk pages, you also have a buffer, shared buffer. This is what we call a shared LRU mechanism, which is shared and follow the LRU for the buffer replacement. And those are accessed with some shared LW lock among the processes, because we need to write into that information, because anybody who is allocating a subtransaction ID need to write that data into that. But reader, generally in most of the cases, most frequent cases, reader don't need to look into this SLRU. But in our case, what we are trying to prove here, the problem happens once readers start to look into this. So yeah, let's little bit understand about the visibility check in Postgres. So we have taken the snapshot, and we talked that is required for getting a consistent view of the data. So when that happens, so for understanding that part, we need to little bit look into the visibility check. So when you starting up the query, you have taken the snapshot. Now you are scanning a table. Suppose we are, for simplicity of understanding, we can just say we are doing sequential scan. We are scanning pages. In pages, we are scanning tuple. So each tuple, we need to identify whether it is visible to us or not. So each tuple in PostgreSQL is marked with xmin and xmax. And xmin of the tuple is actually different than the xmin and xmax of the snapshot. That you can say the creator of the tuple is the xmin stored in the tuple. And when the tuple get deleted, if it doesn't get deleted, the xmax is invalid XID. But if it get deleted or updated and new version is created, then the older version is marked with the xmax who have actually updated the tuple. So this is the what I just explained is the pictorial view of that. That snapshot is marked with the xmin and xmax. In between you have the XIP array and sub XIP array. Below that value, everything is visible to you. Beyond that xmax, nothing is visible to you. And this is the typical page format. I will not say this is actually tuple format, but I just put the xmin and xmax field, which is for our interest for this talk. So basically, if you can just pick XIDs and you, for the visibility purpose, whether it is visible to you or not, that tuple, you consult the snapshot. For consulting the snapshot, if XID is falling below xmin or beyond xmax, you have direct decision that whether it is visible to you or not. But if it is falling into this range, we need to look up into this XIDs and sub XIDs information. From that, we can find out that whether if you find that XID into this array, it means it is concurrent to you, because when you took the snapshot, it was running, so you copied into your snapshot. But if you don't find into that, it means it was not concurrent to you, it was committed when you took a snapshot. So now, what is the problem of subtransaction cache overflow when it happens? So a couple of slides before, we just saw that each backend have the information of XID, and they can also maintain a 64 subtransaction ID information. And those information are copied into the snapshot, and we assume the snapshot is complete. But what happens if any backend start more than 64 transactions under it, then we don't have enough space in the backend cache to keep more than 64 subtransaction ID. So in that case, we just mark that backend structure as it's overflowed. That means it don't contain the complete information of the subtransaction ID. And once it is marked as overflowed, when we are preparing a snapshot, and if any of the backend while taking a snapshot is marked overflowed, that means our snapshot is not complete, because you are not keeping all the concurrent XIDs information into your array. Although the XIP array, XID arrays, the top transaction ID information is still there. So we say that XID array is complete, but sub-transaction XID array is not complete. So where we want to go with this information, that when we know that our snapshot is have only top transaction ID information, but sub-transaction XID information is not complete. So what happens is, like when you do the visibility check, and if any XID is falling into in the range of xmin and xmax, it means we need to consult into those snapshot XID array. But we know that subtransaction XID array is not complete. And looking at the XID into pages, you cannot distinguish whether it is subtransaction ID or top transaction ID. So generally, in normal cases, when it is snapshot is not marked overflowed, we can directly look into XID array. If you find there, well and good, we assume it is concurrent to us. If you don't find, we can look into XIP array. And the same thing, if you find in XIP array, we can say concurrent to us, otherwise it is committed for us. But in this case, you cannot consult the sub XID array. You can only consult the XID array. So that means we need to find out what is the XID for that particular given sub XID. A particular given XID, we don't know whether it could be sub XID or could be top transaction ID. So here the PG Subtrans SLRU come into picture, that you got XID from the tuple. Now you need to identify which is the top transaction ID for this. This might itself could be a top transaction ID, but we don't know. So now we need to go into SLRU, and for that is shared data structure, which is getting written by the backend who is generating the subtransaction ID. So you need to take a lock and look into that structure. Another thing is that it may so happen that you might not get all your you might not get your subtransaction what you are currently looking for into the buffer. So you might need to do buffer eviction and get the information from the disk also. So that is the problem of subtransaction cache overflow. And along with that, I have seen that some more problem with that is like if the number of subtransaction, what you create is getting created in form of tree. Like if you have a top transaction, the first subtransaction is child of that, second transaction is child of that, and third transaction is child of that way. So if you create like 64 or like 100, 300 subtransaction IDs, so the depth of the tree will be really, really big. And when you are getting the information of your top transaction ID, you need to traverse the tree from the subtransaction ID what you found from a tuple to all the way up to the subtransaction ID. So that also can be sometimes costly, but that could be costly only in the cases where you are looking the status of actually subtransaction ID. But what I have observed in most of the cases where the people face the problem is you might not be looking the status of the subtransaction ID. Most of the time you are just accessing the SLRU and getting the output as 0. It means the transaction ID is a top transaction ID and you are just facing the problem or getting impacted, but you are not getting real information from the SLRU. You just get the answer that it is top transaction ID. So what is the presence of, what happened in presence of long running transaction? Because when we see the performance with the subtransaction overflow, it was just dropping to, I mean, 50% is really huge, it was dropping to 50%, but once you start a long running transaction, it becoming really, really worse, where like you can see the normal transaction might not able to proceed also in some of the system. So if you talk about the long running transaction, I mean we just assign a transaction ID and either leave it idle in transaction or we do some operation, anything, but you need to assign a transaction ID that we call as a long running transaction. So what happened is, first thing is that a snapshot, the range of, we talked about in snapshot, there is a range of xmin and xmax. Like the smallest, the oldest transaction ID which is running is the xmin. So if there is a long running transaction, if suppose you start a transaction and leave it running for 4 hours, it means the xid or xmin become a very, very old. In between, if you start a lot of transactions, commit them, so most of the transactions are small and short running, they are doing some operations, they are getting committed, everything is fine, but that long running transaction is creating a problem by holding the xmin of the snapshot. The range of the xmin and xmax will become really, really huge if you leave the transaction running for a long, long time. And what is the impact of that? So now, for visibility check, what we need to do, we are picking the transaction ID from the tuple, we are looking into snapshot, and if it is below xmin, you are all good. You just can skip anything, whether it is overflow, don't overflow, you don't bother. But now, if you are saying that xmin is very, very old because of the long running transaction, most of the transaction, most of our, like in my PG bench case, they are doing the frequent updates. So all those transactions which are getting committed and short running transaction, all falling into this range. So for every tuple, we need to consult the snapshot for the XID because they are not falling smaller than the XMIN. So now, fine, we can search into the snapshot very, very fast because we have XID and sub XID and look up into those, it's just a CPU operation. But if there is overflow, we just talk. If there is overflow, we cannot rely on the sub XID array. So we need to look into SLRU, get the top transaction ID, and then we need to look into the XID array. So now problem is becoming worse because of two reasons. First thing is you are frequently falling into the snapshots XMIN and XMAX range, and because of overflow, you are frequently accessing SLRU lock. So that lock become a contended. Along with that, the range of XID what you are consulting from the SLRU is becoming really, really huge. It means your data, what you are accessing is will not be stay in the cache because you are not accessing this all transaction, not consulting the same range of transaction. You are having very wide range of XIDs which you want to look into the sub-transaction. So frequently your buffer will get replaced out, and so you need, you will be under the lock, you will be frequently hitting buffer replacement problem also, and problem become really worse with the long running transaction. So there is some question around this problem that what happens when we do rollback to save point and release save point. Can we somehow solve this problem or whether the overflow can occur if you keep frequent rollback to save point and all that questions I been asked in the hackers and by customers also. So I just put one slide for understand that also. So rollback to save point is nothing but once you, your purpose of purpose of the save point is that so that if you, is there any problem, you can roll back that operation to a certain point where you have the save point. So if you roll back to save point, that XID, the sub-transaction ID can immediately mark as aborted. Once it is marked aborted, it don't have any dependency on the top transaction ID. It is independently can be assumed as a aborted. In that case, that slot, the sub-XID slot of 64 in per backend cache, we don't need to hold it. So if your transaction is something like that or system is like that, you are frequently rolling back to save points, which generally might not be very common case, then your slot will be released. But that is not true with the release save point. Because many people, sometimes people get confused that if it is rollback to save point is aborting, then release save point is committing the transaction. So there also we should be able to release the slot. But what release save point does is it helps in some way, like it from the stack it releases your sub-transaction structures, and we've also talked about the depth of the tree, that we once we keep allocating the save point and save point, the depth of the tree is becoming deeper and deeper, bigger and bigger. So with, if you keep releasing the save point, the depth will not increase. So maybe while looking into the SLRU, you might not traverse so many slots. From that perspective, it can help. But we cannot consider that sub-transaction ID as a committed, right, independently, because our decision depends upon the top transaction ID. Until the top transaction ID is committed or aborted, we cannot take a decision of sub-transaction ID as a committed. Abort decision we can take independently, but not the commit decision. So we cannot release the slot from the backend cache. That will still hold, and if you keep allocating even after releasing, the system is prone to the sub-transaction cache overflow. So this is summary of this particular problem of sub-transaction cache overflow. Like frequent sub-transaction overflow can create a slowdown in the system. So it doesn't mean that PostgreSQL can never deal with sub-transaction overflow. You can have sub-transaction overflow in which transaction, but like rarely happening, or sometime in the system if it is creating overflow, we can deal with that. Sometime if it is frequently also there, we can, the duration till that you are creating the sub-transaction overflow, there might be some slowdown in the system, but it will not stop working, or it will not halt completely. But with long-running transaction, it can become a worse. Generally, long-running transaction is, I think, considered bad everywhere with respect to many other aspects. But yeah, with respect to this as well, the long-running transaction can create a bigger problem. And yeah, we also discussed that release save point can reduce the depth of the sub-transaction tree. So when you are looking and finding the top transaction, you might not have to traverse multiple slot. You can just find the top transaction ID directly if you always releasing the save point. So this is the first problem introduction, and we also saw that exactly what is happening under the hood. If anybody have any question related to this problem, we can take now, and then we can move to the next problem. Yeah.
Why SLRU is, array like a fixed size? It could have been like a
Why it is
different
not
data
hash or something? Why it is array of something?
or list or something which could actually scale.
Yeah, there is a lot of scope that it could be optimized in a different way. But yeah, currently it is the implementation is that it is of array. So that is also a part of problem, that when you are looking into the buffer replacement, you have to traverse the array and find out. You can directly have the mapping into and find out exactly where. But yeah, that is the current design, and there is chance of improvement in that area. I agree with you.
Yeah, we should have like a variable, something, variable length, like a linked list or something like that.
Oh,
so
you mean to say the backend cache of 64?
Yeah.
Yeah.
Is it in the backend or is it in the shared memory?
So there is two things. One is per backend we have the slot of 64 sub-transaction. That is also in shared memory, but per backend have its own control of that 64. Yeah. That is not shared across, but it is in shared memory, so other can read and take the snapshot. So that 64 also, there is some discussion I have seen in Hacker that people assume that we can, it can be a configurable or can be make it bigger, but there is no real conclusion of how big it should be, or sometimes if it is become really bigger and configured to really high, the snapshot arrays might become a really big, because
this also, why per backend? Maybe we can discuss it offline.
Mm-hmm. Yeah, okay.
Thanks.
Okay, so I think we'll go to the next problem, and then we can take question together for both the problem. So this is another problem in my set, which related to MultiZect. So for simulating this problem, I tweaked PG bench TPCB workload to little, instead of having directly update, I have done, I have taken a lock on the row, 4 update lock, then I started a save point, and then I updated the row. The small tweak in the transaction. With that, I have seen the TPCH performance is fine. It was not dropped. Actually, it did not have any impact on that. But then to see the impact, I started a long-running transaction. And then you can see its like performance is as bad as we saw in case of Subtransaction SLRU. Maybe not that bad, but yeah, it's really bad. And what we see in the wait event is MultiZect offset SLRU and MultiZect offset buffers. So what these wait events are and how it is causing the performance problem, again we'll go into some of the Postgres internal system to understand this problem better. So yeah, my couple of rest of the slides will be related to introducing this problem or understanding this problem better. Okay, so the row locking. So regular select statement when we do in PostgreSQL, sometimes there is a complaint like it is a regular select statement does not provide enough protection. Like suppose you want to read the data, manipulate something, and then you want to update those data. It may so happen that your update fails because of some parallel updater or deleter have done something with the data. So if you want guarantee that if you want to read the data, do some work and update it, and if you want guarantee that update need to be successful, that time the row locking can help. So we provide a different way of different lock levels of row locking. generally most commonly used like select for update and select for share. So select for update is generally used where you can just take an update lock so that nobody else can modify your data, and you're guaranteed once you have the update lock, you can just go and after that lock, you can go and update the data. And select for share lock is more common when we want like, if for example, there could be multiple use cases, but in one most common use case is suppose you have a primary key and foreign key table, and if you are doing some operation, if you want to insert something in foreign key table and you already know that that tuple is already you read from the primary key table, you can take a share lock, select for share lock, and then do some operation in the foreign key table, so that while you are doing the operation in the foreign key table, it should not fail. Nobody should remove that table from the primary key table and then you realize that once you are doing on foreign key table, it got deleted. So for that purpose, row locking is useful. So now for understanding our problem better, let's see how row locking getting implemented. So we know from the previous problem that what is xmin and xmax. We keep xmin as an inserted xid and xmax as a updater or deleter transaction ID in tuple. But now, what about the transaction ID of the lockers? We have got the lockers now, select for share. So there could be multiple lockers in the same row. So that also we maintain the xmax field, but little bit differently because there is limited space. We have just 4 byte space for the xmin and same space for the xmax. But once we have the multiple transaction ID, how do we store them? So for storing them, we got a concept of MultiZect. So MultiZect is provide a way of creating a new kind of XID which we call a MultiZect ID, which is nothing but giving you a representation of XID so that you can directly store into tuple and assume as a XID field, although we have flag to identify that this XID, Xmax is a MultiZect ID, and under the hood it is nothing but a mapping from that MultiZect ID to a number of XIDs and their status, like in what status, what mode they have taken the locks and all. And here also we have SLRU implementation, which we can say PG MultiZect Manager or SLRU. This stores an array of multiple members or XIDs and for which are mapped from the one MultiZect ID. So we'll understand this more in detail. So the number of XIDs, for each MultiZect ID, the number of XIDs are not fixed. So number of XIDs are not fixed. The variable number of XIDs. And due to that reason, we cannot store directly under the one SLRU. We are having the 2 level of SLRU. So first SLRU where we can point MultiZect ID into the offset, and the offset is the actually pointing into another SLRU where we are storing the actual XIDs and their status for the MultiZect. So just to understand better, we can see this diagram. So this is the first level of SLRU where we have directly MultiZect to a slot mapping, and this slot we are storing only the offset into the another SLRU where we have variable number of XIDs and their information in what lock mode they have taken the lock. So when MultiZect ID is actually created, so we saw our example like when we have select for share or different other mode like no key update. No key update is give you protection from like you will not update the key column of that particular table, and the select for key share will take a lock on the key. So no key update and the key share is one of the, you can take in combination for the example what we talk about like primary key and foreign key table, how we update the foreign key table by holding the lock on the primary key table. So, and there is a special case what we have used in our example, like it is not only the select for share or no key update or key share can create MultiZect. There is also a special case where the 2 transactions within the like top transaction and the Subtransaction itself can create a MultiZect ID, because they are not contending with each other, the top transaction, the sub-transaction ID. So you can do the select for update lock in the top transaction ID, and in the sub-transaction, you can update the row. So there also we can create the same sort of contention. So in general, what we saw is like that shared lockers, with the shared lockers, we are creating a MultiZect ID. And what is happening with the long-running transaction is like, when you have the long-running transaction, the hot chain cleanup become really, we cannot clean up the hot chain. So it means number of, the older version of the tuple are keep accumulating. And now if you want to, if reader want to get the status of the tuple, and the tuple are marked with the MultiZect, you need to traverse each version of the hot chain, and for each version you need to access the MultiZect SLRU. So that become a contention on the MultiZect SLRU. And since you are accessing the information of the long range of the transaction because of the long running transaction, this contention also become bad because of buffer replacement along with the contention on that lock. So yeah, this is all about my talk, and we can take a couple of questions. Yeah. Pinar.
Hello.
No.
In case of nested save points, the problem comes because the older save points are not released. Okay. If we have an option like create save point and release all the previous save points, that will be a good option, right?
If you release the save point also, the problem will not be solved completely, because some part of the problem will solve, because I told that there is a tree of the status. You need, if you want to get the status of, if you want to get the top transaction for the sub transaction, you need to process that tree. That is just a small factor of the problem. The major problem is that you need to access the SLRU. So if you keep creating the save point, even though you release it, we cannot consider them as committed until the top transaction is committed. So we need to keep that information into the cache. And if it crosses the 64 save points, even though you are releasing all the save points, still we have to mark that backend's cache as an overflow, and the save point, the snapshot, whoever concurrently taking the snapshot while that backend is running and overflow is in progress, that time that snapshot will be marked overflowed. It means you need to look into the SLRU. That is not avoided, but depth of the tree can be little smaller.
Yeah. Suppose there are 10 save points or something, and if we want to create a new one, if the 9 of them are removed, it will be better, right? The depth
yeah, so right. If the two things, one is that depth of the tree will be smaller, and if you are looking of the status of those sub-transaction, then you are escaped. But in my test, what I presented, we are, there is only one transaction which is creating the overflow. And if parallelly there are a lot of operations happening, which is just happening in the top transaction ID, they don't have any depth of the save point or something. But for these transactions also, we need to look into the SLRU. So that becomes the most of the reason and cases where we observe the problem is like the transaction whose status are getting access are not actually creating the overflow. They are just normal other transaction, and they are mostly top transaction only. So there is no depth of the tree. They are getting impacted because of we don't know whether there is a sub-transaction ID or not.
I was thinking like if that option was there in PG, it would have been a good thing.
Yeah, release is, can help
save
in some
point
cases.
along with the release older ones like that, if there is an option for that.
Okay, currently the option is not there. User have to do their release their own. They can release save point. Yeah. So I told you, if you are getting the status of sub-transaction ID and very, very deep sub-transaction ID, there it can be some help. But yeah, very rarely it can help. Okay, thank you.